Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, lecture 99, continuous charges and field lines. So last time we talked about distributions of a small number of charges, like 1 or 2 or maybe 3, okay? But what if we have a whole lot of charges, right? Let's say I have charge, call it Q1. Maybe over here I have charge Q2, and then charge Q3, and then over here maybe charge Qi, okay? So there's a whole bunch of them. I'm not going to write them all in, right? So what does the electric field look like for that on some test charge at some arbitrary point? Actually, I wanted to write E, not sigma yet. We would write that the electric field is equal to, that's a sigma notation. Do you remember that? It's for summing, right? Yeah. I, and we would put, we'd have K out front because that's not going to change from term to term. And we'd have Qi over, I'm going to call it Ri naught squared, Ri naught hat, okay? So that's just, if this is my test charge point, right, then this vector here is Ri naught, okay? So this sum just means do what we did last time where we said the electric field was equal to E1 plus E2, right? And we sum it up for every charge we find. And we start at the first charge, right, Q1, and we work our way all the way up to the ith charge, okay? And because of the superposition principle, the electric field will be a single quantity, though it's a vector, okay? And that makes sense, right? Yeah. But that's a sum, so that's a lot of summing to do, right? If we had, like, say, 10 to the 23 charges, would you want to do 10 to the 23 sums? No, you would not, right? So what happens when we have so many particles and they're roughly evenly spaced and it's kind of homogeneously distributed, right? Like you might have on, say, a wire, right? Well, in that case, we're going to turn our sums into integrals, okay? Over volumes, if it's a three-dimensional space, like I'm asking what's the charge on this, sphere, right? Or it could be an integral over an area. If it was, say, the charges that are distributed on a flat sheet of metal. Or, of course, it could be the integral over a single direction. So if it was, like, say, a wire, and we're treating that wire like a 1D object, right? Yeah. But, of course, the thing that we need, how do we get the charges in? Well, we can represent this sum of the charges, right, by a density, okay, a charge density. So we could have, so the standard is rho is the density in terms of 3 dimensions, right? So that's charges per meters cubed, for example, okay? And so that's just Q, call it total, divided by the volume, okay? We could also have, for areas, the standard the standard symbol is sigma, lowercase sigma, and that is equal to Q total divided by the area. So if we were, for example, if we had an even distribution of charges on a sheet of metal, and we knew what the surface area of that metal was, then we could talk about the total charge, take the total charge on the sheet of metal and divide that by the area of the metal, and that would give us this sigma, this charge per unit area. And finally, the standard symbol for one dimension is lambda, and that is Q total divided by, what's called L, the length of whatever the 1D object is we're talking about. So if I have a wire and I have 10 charges on it, and it's 1 meter long, the charge density is 10 coulombs per meter. Okay? Does that make sense? Yeah. And so you would use these quantities inside these integrals, which have replaced these sums. So instead of adding up the individual charges, we're going to now integrate, and we're going to use these continuous charge distribution numbers. Okay? Densities. Okay? Do I want to say anything else about that? Well, let's see. So what does our electric field look like then? Then, for example, in a three-dimensional space, our electric field might be given by something like this. The integral of K times rho divided by, we'll call it Ri naught squared. And that's a vector, of course. Ri Well, I guess we're not adding up anymore, so I'm just going to call it R. Okay, so R hat. Okay? So that would be the integral we need to do. Not going to lie, these can be troublesome. It's almost like every particular geometry has its own, different approach to solving this. Okay? But I'll go through one just to show you what it looks like. Okay? But let me draw it on the board first. And that's going to take a minute. So, okay, so here I want to consider a line charge, an infinite line charge. Okay, so we're doing basically a two-dimensional problem here where I've got a line of charge which goes on all the way to minus infinity and all the way to plus infinity. And the charge density is uniform, and it's given by some lambda, right? So lambda is our charge density. That tells us how many how many coulombs per unit length we have, okay? And what I want to do is I want to consider, to begin the problem. Here's how, usually the way these problems begin is like this. I want to find a little delta Q, right? So what I want to do is I want to say something like delta E. Oh, you know what? Before I say that, let me just point out, because of the symmetry of this thing, right? So if I choose this little region here, right, and think about what does the field look like at this point P, where our test charge is, which is up here, what does the field look like due to this little region of charge distribution here? Right, you can see what it's doing. It's kind of acting like this, and it's got two components. It's got an x component going in the negative direction, and it's got a y component going in the positive y direction. Does everyone see that? Because it's acting like this. Yes? So component going like this, component going like this, right? So this little region over here, yes? But similarly, if you took a symmetric look at the same distance away from the center here, or really where my test charge is oriented here at this point, right? If I look in the same distance away in this direction, we get exactly the same thing, except this time the x component is facing the opposite direction. You see that? So here the x component is pushing it this way, and then from this side it's pushing it this way equally. Okay? So those x components completely cancel. So you can say that, E sub x, I don't know how to best write this, but we could maybe say, from the right, so I'll put like a plus sign, right? When you come from the right, that's equal to the same thing that you get from the left, except it's the negative of it, right? E sub x when we look at it from this way, right? So they're equal and opposite in sign, which means they completely cancel out, so we really only need to consider the y component, okay? So this little bit of field that we get in the y direction from this section here, right, or any particular section, is going to be equal to k, the proportionality constant, times some delta q, right? That's the bit of charge that's in this region that we're looking at, okay? Divided by this length right here, s squared, okay? Times the cosine of theta. Why times the cosine of theta? Because this is the field that we get from this little region here, but we want the field only in the y direction, okay? So we take the cosine, we take this, the electric field, times the cosine of theta. Do you see that? Because it's adjacent over the hypotenuse, right? Yeah. So we want to times the cosine of theta. So what often happens in these problems is you want to figure out what this delta Q is, okay? And so here we're going to treat it as, so what is delta Q? This little region here, if we look at a little delta X, okay? And I probably should have said it, but this is X, this is Y, okay? This little region, delta X here, right? Well, how much charge does it have in it? Well, it has delta Q is equal to lambda, the charge density, times delta X. Because remember, delta X is some number of meters, let's say, right? Lambda is charge per meter, right? So if I multiply these two quantities together, I get some little bit of charge, right? So that's telling me how much charge is in this little region right here, delta X, okay? Okay. Now don't worry about where you start delta X at and go to, right? This is very small. We're going to let it go infinitesimally small, so that really it's going to correspond to where this point, this line S is reaching the line of charge, okay? So we can then write that this is equal to K over S squared times the cosine of theta. And delta Q is now going to be written as lambda delta X, okay? And so the reason you want to get this delta q so that you can get this delta x, because you need something to integrate from, okay? And so what do we always have? One more substitution we can do. The cosine of theta, what is the cosine of theta? Well, the cosine of theta is just equal to y over s, yes? So if I substitute that in, right, that's k over s squared times y over s times lambda times delta x. And so finally I get that delta E sub y is equal to k y over s cubed times lambda times delta x. Okay? And so what we want to do is we want to do an integral. So if we think of doing a sum, we'd say, well, let's just add up all these little delta EY's, right? Yes? Yeah. So we would say, well, it's, so EY would then be equal to the sum of all of these delta EY's, right? But we are going to, because it's continuous, we're going to let these guys become a DE, right? And this becomes a dx. And so now our EY is equal to the integral of DEY, which is just equal to equal to EY, okay? So let's write that out here, EY. There's one more little bit of symmetry that I'm going to exploit here, okay? And that's the fact that I'm going to go from 0 to infinity instead of minus infinity to infinity, okay, to add all these pieces up. Because if I just go from 0 to infinity, then I just have to multiply everything by 2, because it looks the same on the left, right? Yeah. So I'm going to write this as EY is equal to 2 times the integral from 0 to infinity of k y lambda over s cubed dx. Okay, so problem, I don't have any x's in here, do I? Now I could substitute in for this, right? And so that would be the next thing we would look at here. So let's see, what does s cubed look like? Well, we know that s is equal to the square root of x squared plus y squared. Everyone see that? X squared plus y squared, that gives me this s, square root of that, right? Just the Pythagorean theorem. But I want to cube this, so I have to cube it, right? And it looks like this. But I want to make a few changes to this. Let's write this like this. S cubed is equal, I'll put it in parentheses. I'm going to factor out, let me see, what do I want to factor out? Yeah, I want to factor out an, hang on, one more time. This would be the tangent of theta. So I want to exploit this. The tangent of theta is going to be equal to the opposite, that's x, over the adjacent, that's y. So I want to divide out a y. So I'm going to pull out a y squared, like this, times, that'll give me x squared over y squared, plus 1. And this is all to the 3/2 power, right? Because I had that square root, so I just put it as a fractional exponent, yeah? So the square root cubed is just the 3/2 power, yes? Does that make sense? Yeah? And what I've done is I've factored out the y squared, right? So if I multiply it through by this, that'd be y squared times x squared over y squared would just be x squared, plus 1 times y squared would just be y squared, so I get x squared plus y squared back, yeah? Okay. But of course, this is y squared, and the square root of that is just y, so I can write s cubed is equal to y cubed, right? Times x squared over y squared plus 1 to the 3/2 power. Yes? Because y squared to the 3/2 power is just y cubed. Yes? Because the square root of y squared is y, and then you have to cube it, so it's y cubed. So we get that. But x squared over y squared, that's just the tangent squared of theta, yes? You see that? If I square the tangent, then it's x squared over y squared. So that's what this is. And so this, s cubed, is now equal to y cubed times the tangent squared of theta plus 1 to the 3/2 power. Okay? Yeah? I'm telling you, these kind of problems are just a little bit of torture that all physics professors put on freshman physics students when they take their Physics 101 and they get to the electricity and magnetism portion. Tons of little problems just like this, equally annoying. So a lot of rigmarole we have to go through here, right? So we're not done yet. But if you were to consult a table of trigonometric identities, you would find that the tangent squared of theta plus 1 is equal to the secant squared of theta. Okay? Now why is that nice? Well, because I got a square root. I can take that square root and I'll end up with like a secant cubed, right? So if I recognize that the tangent squared of theta plus 1 is equal to the secant squared of theta, then I can make a substitution in here, right? And that will give me that s cubed is now equal to y cubed times, well, the square root of the secant squared is just the secant. So that's the secant cubed of theta. Okay? This is how we write cubes and stuff with secant, with trig functions. We always put it before the angle, but after the function name. It's just a weird thing. But okay, so that's something. Let's put that in and see if that gives us any progress here. E sub y is now equal to 2. And I'll go ahead and pull the k out because that's not going to affect the integral, and the y as well. The y is fixed. I'm fixing this test charge here. I'm not moving it around, okay? So I really just want to know what the field is at that point, okay? So y I'm going to pull out. But I've got a y cubed that is going to be in the denominator of this. But maybe I'll just write it in and we'll pull it out one at a time here. 0 to infinity. I guess I could pull the let's pull the lambda out, because that's not going to change anywhere. And so I'm going to get just a y here, and I'll get the y cubed down here, and the secant cubed of theta here, and we still have the dx, yes? But I can cancel this y out and change this y cubed to y squared. Okay, so that's something. Since it's going to remain fixed, I may as well move it under here. So let me just move it under here. Okay? All right, well, it looks a little bit better, right? Now, we know what the secant of theta is, and I could make it, because the secant of theta, right, is equal to 1 over the cosine of theta. Right? I could make that substitution now, but I'm going to wait because I've thought ahead on this, and so I know where I'm going next. Because we have an integral, and we have something that's a function of theta, but we're integrating with respect to dx, okay? I can't do that. I don't know how to integrate theta with respect to dx, so we would like to have a d theta here, right, so that we can add it up for every possible angle, right? We'd like to go from, if we're going from 0 to infinity, we would go from the angle 0 to pi over 2, okay? That's what that angle would be out at infinity. It would be pi over 2, or 90 degrees, right? So we're going from straight down to 0 to 90 degrees. Is all the way out there at infinity. That's the angles that we're sweeping out, yes? Yeah. Can you see that? Yeah? But we don't have this in terms of, d theta. We have a dx, right? So here's what we're going to do now. We're going to say, oh, well, our function over here, tangent of theta is equal to x over y. I could rewrite that and say, well, x is equal to y times the tangent of theta. Yes? It's just solving for x. Yes? Now I know how to take a derivative. So I'm going to take a derivative with respect to theta of this. I'm going to take dx d theta. And what's that going to be equal to? It's going to be equal to y times, because y doesn't depend on theta. It's a fixed quantity, right? Times the derivative d over d theta of the tangent of theta. And that is one of the derivatives that I can look up in a table. It looks like it should be pretty easy. Not all of them are, but well, the derivatives are, but some of the integrals can be not so fun. But if I look up what the derivative of the tangent of theta is, I will find that it's equal to the secant squared of theta, which is why I left that secant cubed in. Okay? So dx d theta is equal to y times the secant of secant squared of theta. Okay? So let me do the thing that mathematicians hate. Okay? I'm going to treat dx d theta as if it was a rational number, right? And I'm going to write it as dx equals y secant squared of theta d theta. See that? See what I did there? Mathematicians hate that. They say you're not supposed to do that, but I say phooey. It works, so we're always going to do it until it doesn't work. But I think it always works. Maybe some case where it doesn't. But and I'm going to replace dx with this quantity here, because now I have my d theta. Okay? So I plug that in. I'll get e sub y is equal to 2k lambda over y squared times the integral. Now, no longer is it going to be from 0 to infinity, because now my variable of integration is theta, right? So I'm going to go from 0 to pi over 2. So I change the limits of the integrand from 0 to infinity to 0 over pi over 2. 0 to pi over 2, okay? And I'll get y secant squared d theta, so y secant squared of theta d theta, but I still have my secant cubed of theta in the denominator here, right? I see the y here, the y squared down here. I can cancel this y out and get rid of that square, right? Secant squared over secant cubed, that's just secant, right? So I get that. And 1 over the secant is just the cosine, okay? So I can replace 1 over the secant of theta with the cosine of theta. And that's really nice because that's one of those integrals I can just look up. Actually, I think I gave you, no, did I give you the integrals for the trig functions? I think I did, for most of them anyways. And I know I gave you the derivatives of the sine, the cosine, and I think I gave you the integrals of the sine and cosine because they're related. They're anti of each other, right? So the integral of the cosine is just the sine, as it turns out. And remember, the limits of integration, that's where we evaluate it at, right? We're taking the area under a graph, right? But we're going to start at, say, the origin at 0, and we're going to go out to some value, in this case pi over 2, okay? And that's where we're going to look, that's the area we want, okay? So what do we get? Hope I get this right. E sub y is then equal to 2k lambda over y times the sine of theta evaluated from 0 to pi over 2. Okay, and so that's going to be equal to 2k lambda over y. That's a terrible lambda, by the way. So we have the sine of pi over 2 minus the sine of 0. Okay, what is the sine of pi over 2? The sine of 90 degrees. Anyone remember? 1, right? So the sine of pi over 2, that's 1. The sine of 0 is 0, right? So my final answer, squished down here at the bottom, is that E sub y is equal to 2k lambda over y. And I'll kind of circle it like that because it's really getting squashed. So man, that was a lot of work, wasn't it? And it, you know, this is, I wouldn't say it's a really easy one, but it's pretty easy. There are much harder ones to work, okay? But this is how you do a simple problem, okay? And now in the homework, I'm going to ask you to take this result, basically starting from here, and instead of considering an infinite line of charge, to consider a finite line of charge that goes from minus L to L, okay? And so this is where you'll do that work, right here at the very end. So you don't have to rederive all of this. You'll start with this result, but you're going to have to think about how you're going to change the evaluation of it in order to calculate what you would get for a finite line of charge from minus L to L, where the test point is centered at the center of the rod. It wouldn't work if you moved too far to the right or too far to the left. You'd get some other effects. You wouldn't have that symmetry for the x components and canceling out, okay? So, yeah, so that's, yeah. So it's a mess, isn't it? Yeah? So this one, once you get into, you know, kind of the second semester of calculus, you start doing a lot of integral problems, and these are great exercises to do integral problems with. You see a lot of trigonometric substitutions for these kind of problems, but yeah. So a lot of work. I'm going to show you a way, not this lecture, but next lecture, on how to solve these problems very, very easily, okay? So we'll use something, a principle, that will make doing these kind of things much easier. But I wanted to do this problem so you can see what's involved in working it out, okay? Also, just think about what the result is saying here, right? So, for starters, is it at all surprising that an infinite amount of charge is not going to create an infinite force? That might have been your first guess, right? That, well, if I have an infinite amount of charge, I have an infinite force, right? Well, remember, that drops off like 1 over r squared, right? So, charges very far away are not going to contribute much to the field at this point, right? Because it's very far away. So remember, it's going to scale like 1 over s squared, right? So the contributions from stuff very far away becomes minimized pretty quickly. It seems to be inversely proportional to this distance from the line of charge, right? So if you're really close, this could be a very strong field. Whereas if you're really far, it's kind of scaling off like 1 over r as we move away from it, okay? Other than that, it's proportional to the charge density, which makes sense, right? If I double the charge density, I would expect doubling the, you know, the force that my test charge will feel, right? So that makes sense. But you should definitely think about the results that you get and whether it makes sense to you, okay? Like in the last problem set, we had a dipole problem, and if you were able to come up with the equation that I said to derive, then you of course want to think about, well, why is it that that equation makes sense? And the result is that along the dipole axis anyways, the field drops off like 1 over r cubed instead of 1 over r squared. So it falls off much faster than it does for just a point charge, right? Well, it's a dipole, so it's kind of the two charges at a great distance, of course, is 0, for which you expect no electric field. So it's not surprising that the field is going to drop off faster, since at a great distance it would be 0. Okay? Yeah? So it's that shielding that it's doing that's kind of causing it to drop off faster. And of course, if you were to look in the other directions, right, not along the axis of the dipole moment itself, but perpendicular to it, you would find instead that it drops off like 1 over r to the 5th, so even faster. Okay? But I don't think I put that in the homework assignment. Let me just mention some other charges, and I'll make some space here so we can write some stuff down. Maybe I'll just put what this turned out to be. So this, for the line charge, it turned out to be E sub y was equal to 2k lambda over y. My lambda's looking like a y. Other things that you consider, or could consider, instead of a line charge, what if I had an infinite sheet of charge, right? That's one we'll actually do, and you'll be surprised at how easy it is to find the answer. We're not going to do it this way. We're going to do it using a trick. But if we were to do it this way, what would we find? We would find that, so this is line charge, infinite plane of charge. There are probably better names for this, but so E sub y for an infinite plane of charge would be equal to, I believe it's 2 pi sigma, the charge density. It should have a k in there though, right? Oh yeah, of course. 2 pi k times sigma. Okay? So that's a little weird, right? It seems that it's just as strong no matter where you are, right? It doesn't matter how far away you are, it has the same field strength. It's only proportional. It's really just, what's the dominant term? These are just constants. It's just proportional to the field strength. So no matter how far away from this infinite plane of charge I am, I still get the same electric field. That's weird, right? So we didn't see that with a line of charge, but we do see it with a sheet of charge. That's what I should have written, sheet of charge. Okay? What else? A sphere of charge. Oh, actually, I'm going to write just E sub r here. Well, this is for r greater than big R, where big R is the radius of the sphere. Okay? It looks like a point charge. That's kind of interesting. Now, Isaac Newton spent, I think I heard that it took him 20 years to come up with this result. Because this applies to gravitation as well. If we're talking about gravitational fields, right? That would be more like if these were negative charges instead of positive charges like we had done in the past. But yeah, same result for a sphere, a gravitational sphere, right? If it's a shell, you get an interesting result. If it's a solid object, then the field inside the sphere just is linear from the distance to the distance from the center. Okay, just increases linearly until you get to the edge of the sphere, and then it starts dropping off like 1 over r squared, like a point charge. Okay, but if it's a shell of charge, then and it's a hollow shell, right? That's what I mean by shell. Inside the sphere, the electric field is 0. Okay, so this is related to what we call a Faraday cage. Right? It's a way to shield yourself from electromagnetic signals. You used to see it whenever we listened to radios that had signals that were propagated through the air. I guess most people use satellite now, but if you were to drive over a bridge like in San Francisco, it's got all the wires and metal, steel girders up there. It's basically a Faraday cage, and your radio reception would drop off to almost nothing as you drove over the bridge. You're like, in New York, there are bridges that are like that too. You feel you get to experience that loss of radio signal. I suppose it would apply to cell phones too. But I, of course, don't talk on a cell phone when I drive. Good safety tip. But I do listen to the radio, or I used to anyways. So these are some standard results, but we will find another way to come up with these solutions for the electric field in a much easier fashion. Okay? Okay, so that was the continuous charge part of the lecture. Now we're on to the field line part of the lecture. And the field line thing is kind of neat, okay? It's a graphical technique to think about this. It has its origins in lines of force as postulated by Michael Faraday. He was a contemporary of James Clerk Maxwell. And he was a very smart guy, but I think he was mathematically, his powers were limited. His training was as a bookbinder, which is where he got interested in physics. I guess he was reading the books he was binding. But his math skills weren't so hot. But he was a very intuitive thinker, and he came up with these ideas of field lines, Really, he called them lines of force. Now we're going to call them field lines. It's not quite the same as it was before, but so let me show you how that works. So if I think of a positive charge, so there's basically some rules for these. Have you ever seen the thing that you do with the magnet and the iron fillings? You get a magnet, and you get some iron fillings, you lay them out, and then you put the magnet close to it, and you'll see the magnetic field lines, right? We'll probably do that demonstration later. I wanted to do a demonstration to show you electric field lines, but I could not get a, well, I ordered a wind source generator, but it was broken. It takes a, you got to put a lot, you need a lot of voltage. But you can do it with grass seeds in, mineral oil or vegetable oil or any kind of oil, and you can, you'll see these field lines. Let's think of it as a way to draw the electric field, but there are some rules, okay? Rule number one, field lines begin on positive charges and they end at negative charges, okay? So they'll have arrows. And so here we have a positive charge, and we're going to draw some field lines for it. Rule number two is that we draw the field lines symmetrically, okay? So we use that as a guiding principle. This is not an exact science, mind you. Number three, the number of lines within a given area is proportional to the field strength, okay? So, for example, if these are my field lines, right? This electric field is much stronger than, say, this electric field, okay? Because in the same area, there are more field lines, you see? Yes? And the only other real rule is that field lines can never cross. Because if field lines cross, that means that at some point, the electric field could be going in two different directions. And there's only one direction, okay, at any given point. So field lines can never cross. So here's just a simple positive charge, okay? And I'll say that this is a charge of, let me write it as +1. +1, okay? Since it's positive, field lines will leave from this, okay? So I'm going to choose to represent this with 4 field lines. Now I want to double the charge. I'm going to make it +2. If I imagine a circle, this circle has got some surface area, right? Well, this is not a sphere, so this is a line, so it has a circumference, right? And so if I were to calculate the number of field lines that pass through this line, that's 4, right? Divided by the length of this line, which is 2 pi r, right? It's the circumference of that circle I've drawn. I'd have 4 per that distance, right? So if I have +2, I should have twice as many. So I would have to double the number of field lines I draw. Let's look at another thing, though, right? If I were to look at a closer point, right? So let's say that this is, as we have it drawn now, I'm going to consider this at some distance r, okay? What if I drew another circle around here? Yeah? And this is at a distance little r, let's say, okay? You can see that the density, right, the number of lines per unit line length, right, has gone down as we get farther away. Yes? That's saying the field strength has decreased, like 1 over r. Well, that is if we're talking about a two-dimensional geometry. And if we were working in a two-dimensional world, that is how field lines decrease. They decrease like 1 over r. But now let's imagine that this is just the cross-section of a sphere, okay? Such that this little circle is just the cross-section of a little sphere of radius little r. The surface area of that sphere would be 4 pi r squared, right? So here I've got, at this point here, let me write my field magnitude. I'll write at r, little r, is proportional to, and that's 8 field lines, 8 over 4 pi little r squared. Yes? Yeah? And if I look at the magnitude of the field out here at big R, right here, the electric field at big R is proportional to, got 8 field lines still, 1, 2, 3, 4, 5, 6, 7, 8, right? Divided by 4 pi big R squared, where big R is bigger than little r. So you can see that this idea of a 1 over r squared law is kind of natural, right? Think of these field lines as like light rays emanating from a light source, yeah? The farther away from the light that you get, the dimmer the light is, right? If I'm up close in my eyeball, right? Rays, right? If I put my eyeball like right here, right up close, yes? You can see I've got 1, 2, 3, 4, 5 field lines hitting me, yes? So I could call that bright. If I were to then move my eyeball back farther away, so I allow these lines to continue to go out, I put my eyeball out here somewhere, now I'm only getting 2 of the lines hitting my eyeball, yes? So my perception is that the brightness of this has gone down, right? That's because I'm seeing fewer light rays at a distance than before. How much did it go down? It went down by 1 over r squared. if we consider this to be a three-dimensional space, okay? In 2D it goes down as 1 over r, but in 3D it goes down as 1 over r squared. So does everyone understand this relationship between the field line density and the magnitude of the electric field? No? Well, can you imagine this little sphere being here in the center? It's like a globe, right? It has radius of little r, yeah? How many field lines pass through its surface? 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6, 7, 8. 8, right? 8 field lines. So that's 8 field lines per, let's just drop the 4 pi, right? And we'll say that r is equal to 1, so that's over 1 squared is 1, yeah? That's here. That's the magnitude of its electric field. Or at least it's proportional to that, okay? What about out here where r is, let's say, 2, okay? Again, we'll ignore the 4 pi, so now we get 8 still, because it's still 8 field lines passing through this surface, right? But we are at, what did I say? Did I say 2? Big R is 2? I think I said big R was 2. So that's 2 squared, right? So that's 8 over 4, which is just 2, right? So I started out, I had a magnitude of 8 here, and a magnitude of 2 here. You see? Because this is a bigger surface area, right? It's a big globe. It has a much larger surface area. The amount of paper I have to get to cover that globe is greater, right, than the little one, yes? But the same number of field lines pass through it, right? Yeah. So like I said, the electric field is proportional to, that's the way we've represented it, okay? We've drawn it this way on purpose. So we represent the magnitude of the electric field as the density of the field lines over a surface, okay? And so it captures our 1 over r squared notion, right, for this +2 charge that I've drawn here, yeah? All right, let's look at a few more distributions. Because here I only had 1 charge. What if I have 2 charges, right? Let me put a positive charge here, and I'll put another positive charge here. I said that field, so out in this direction, it's not a problem, right? Here's a field line going out. Here's a field line going out, yes? But what about this way? I said field lines can't cross, right? And they have to be symmetrical. You remember that? So these field lines, they'll tend to want to come out straight like this, right? But what they're going to do is they're going to bend up in what should be a symmetrical fashion. And they do the same thing here. We can think of like the field line that should have gone straight across is split it into 2 field lines like this. Now you can see the general tendency of this, right, is for these field lines to kind of do something like this. Something like that, right? So here's a computer-generated version of that, right? It's a little better as far as the symmetry goes. This would be kind of close up like I've drawn it here, right? So we see here's a +1 charge, here's a +1 charge. You see how the lines are symmetrical, and they avoid each other, and they never cross, okay? If I were to zoom out, take a larger picture of it, right, you can kind of see that when you zoom out, it's starting to look like a single point charge, right, that's radially symmetric in all directions, okay? And that's because at a great distance, that's exactly what this is. It's going to behave just like a single point charge, right? If the distance that you are away from it is big compared to the distance of separation between them, then that's what it's going to look like. It's going to look like a +2 charge. But what if I change the sign of this? Let's look at that dipole that we talked about before. Plus minus. So charges leave, or field lines leave positive charges and they land on negative charges. So there's one field line, yes? And you can imagine what nearby field lines are going to do. Like it's going to be something like it was going to go out like it was just a positive charge, but it's going to bend back around, right? And so we're going to end up with something like this, yes? Same thing from the bottom here, yeah? And this is going to kind of continue on in a fashion like this. Of course, out here, we will have a field line like that. Remember, it's going to land on a negative charge, so the arrow's got to go this way, yes? Whereas on this side, the arrow's pointing in that direction, right? And so we'll kind of continue around like this, but this is balanced out, right? The positive and the negative, they kind of cancel each other, right? So ultimately, all of these lines are going to bend back around, okay? So this line here is actually coming back around in here. But you could continue on like this. My field line drawing skills are not the greatest, but here is a computer image of what it would look like, what I'm trying to draw here, right? Far field is going to look like no charge at all there, okay? So that's a dipole. What if I were to replace one of the charges in this dipole with, say, maybe I took the positive charge and replaced it with like a +2 or a +3 charge, right? That would be interesting. And I actually did, this is a +2 -1 charge distribution. I guess this is the negative charge over here. And you can see that the positive charge on the right is kind of wiping this out. You see this? So you still kind of get a little bit of that dipole effect, it looks like, right? But when you're out farther, right, you see that it really just looks like a +1 charge, okay? So I told you before that the infinite sheet of charge had constant field lines, right? It created a uniform field. So how would we draw a uniform field? Like this. See, the spacing between the lines, right, is not getting any closer or farther apart. So this is a uniform field. So that's how we would draw that, okay? So that says that the electric field is just constant. This would be positive charges on this plate. So do you remember what happens if I put a test charge in a field, right? Remember, this is the electric field, right? And if I multiply this times the test charge, what is that equal to? That's equal to the force, right? So for a uniform field like this, right, what's happening to a test charge in it? It's going to just accelerate in the direction of the field lines, yes? Yeah? I think in the homework I give you a problem where I ask you what happens if you were to put a dipole in a uniform field like this, okay? So it's where the dipole is kind of rigidly bound, right? So what you want to think of there, right, is that you've got this dipole, you know, with some distance L between them. Maybe this is the minus charge, this is the plus charge, right? This distance is fixed, so somehow this is held stable, okay? But think about the force on this and the force on this and what the net force is for that and what's going to happen to this rigid body, okay, in this uniform field. So I want to imagine that I've got a couple of metal blocks here, okay? And I can separate these metal blocks. And let's take my glass rod, right, and bring it close to these two metal blocks. So what's going to happen? You remember the metals, right, freely conduct electrons. The electrons are free to move anywhere throughout the metal block that it wants to, okay? So what's going to happen with these two metal blocks touching each other? Feels this positive charge, what's going to happen? All the electrons are going to race over here, and so we're going to have some negative charges over here on this side, right? But if that happens, that means there's going to be a bit of positive charge over here on this side, yes? Because we took electrons from over here and moved them over here, yes? Now, I separate these two. We'll go down here. I separate these two blocks. What do I have? Got some negative charges on here and some positive charges on here, yeah? Separated by some distance, call it L. And then I remove my charged glass rod, right? So what do I have now? I've got myself a dipole, don't I? We talked about that, I think. Well, we may not have talked about making a dipole, but we definitely talked about inducing charges in a metal, right? Using our glass rod that we've rubbed, and through the triboelectric effect, we've lost electrons, gaining a positive charge on the glass rod, right? I want to do it now with just field. So if I said, here's my blocks again, right? And now I'm going to introduce a uniform electric field. What happens to electrons in this metal? Electrons are attracted. So remember, field lines come out of positive charges, so you can think of this being the result of some positive charges somewhere, right? So the electrons are going to be attracted this way, right? And in doing that, that's going to cause the right-hand side of this to be positively charged, such that if I now separate these two blocks, just like before, and then I remove the field, turn the field off, right, I've got a dipole again. So this was a result of the charges moving in the field. And the last thing I want to talk about is molecules. Yeah, so most molecules are nonpolar, meaning that their center of charge, of positive charge and negative charge, coincide with one another, all right? But what happens if you put a nonpolar molecule in an electric field? What's going to happen to it, right? The electrons in this molecule are going to wind up on this side, leaving the protons on this side, and we've done what we've created a dipole, haven't we? We've induced a dipole, yes? So now is it going to go anywhere? In this uniform electric field, it did get stretched, it made it into a dipole, yeah? But because the field is uniform, right, it's pulling as much on the negative charge as it is pushing on the positive charge, and so the net result is it doesn't go anywhere. Okay, so we've induced a dipole, but the molecule hasn't gone anywhere. It's not going to accelerate. Okay, so in the homework I asked you to consider the case where you have a non-polar molecule in a non-uniform electric field. What happens? Okay, so you have to think about that and see if you can figure out what's going to occur in that case. All right. Okay. Finally, if I turn the field off, what happens to the dipole? Does it stay or does it go? So now I turn the electric field off. What happens now to this non-polar molecule? Well, now I've got this negative charge and this positive charge separated. Before it was separated because you had this field stretching it like this, right? The field's not there anymore, so it's no longer stretching on it. So now the positive charge and the negative charge go back to coinciding again, right? Right on top of each other, right? And so, well, I guess I should just draw it. So I no longer have my dipole. The induced dipole disappears as soon as I remove the field. Now, we probably will talk about the electrical properties of different materials, the dielectric properties of matter, and we'll talk about different types of like ferroelectricity and stuff like that, paraelectric materials. But for now, nonpolar molecules, that's what's going to happen, okay? So the field lines are a useful way to try to visualize what's going on. One last thing I'll leave you with is that when you draw a surface, right, the field lines will always emanate perpendicular to the surface, okay? So if I have some surface like this, and it's charged, right? Let's say it's positively charged. Which way do the field lines go? They go perpendicular to the surface. You see? If there are charges on this face, they're going to, well, that's not the right way to draw perpendicular to that surface. They're going to be perpendicular to this surface, right? So I'll draw little perpendicular signs there. You see? If I have a spherical surface, there are charges all on this surface. Which way do they go? They'll be normal to that surface, which means they emanate from the center of the sphere. You see? Because radial lines are always perpendicular to tangents on the surface, right? They're always perpendicular to the surface. If it was a cylinder, it'd be the same thing, right? How do you figure what the field, if I put a cylinder where the center of this is this point here, right? What does the electric, and this is, a cylinder, and I have electric charge distributed throughout the surface, right? What does that electric charge look like? Well, it's always going to be coming out, so I'd like draw something like this. It's always going to be normal to that surface. You see? That makes sense? Okay. All right, any questions? You have a lot of questions. You're just going to wait till after we're done with the filming and all that stuff, and then you're going to bug me for hours asking me questions. I know. Okay. I think that's it.